that, why don't you go ahead and get started, and then I'll see you when we're doing Q&A.
Thanks so much. All right, folks. So, there's a lot of talk in machine learning about doing machine learning at scale and doing it in the real world. And it's one thing to kind of do it, in an academic environment or by yourself or a couple of people. But when you start building a larger team, there's a whole series of infrastructure that's really necessary. And there's a lot of different companies that are starting to pop up and a lot of open source tools. So really, how the heck do you make sense of all of it is really the big question. So I'd say there's a huge AML landscape. It's super vast, complex, it's rapidly evolving. There's a Cambridge explosion of new software and services. There's no clear and reliable guide. And it's just complex to understand. I mean, it doesn't matter if you've been doing machine learning for forever, you went to university, or even if you've been at a number of different companies, the space is evolving so quickly that it's hard to know how to get your hands on it. It's hard to see through the marketing hype and understand what's real. One of the things we did at the AI infrastructure is really, we've got 40 different companies in there. We've got 5 or 6 different communities in there with 60,000 data scientists and data engineers in there. So we strive to be incredibly neutral across all of these different companies, the platforms, and really kind of take a look at the entire industry, understanding what it needs. So we put out this incredibly comprehensive report. It was a huge effort. It's wonderful. It's free. You can grab it right from the link there. I think we're going to put it in the chat as well. But it's going to give the team leads, technical architects, anyone else the keys they need to build and expand their infrastructure. And so they know how to have a kind of clear overview of the landscape, where to put their time and their money. And we did a survey in there of 300 different companies, everyone from small and medium businesses to like multi-billion-dollar companies. And we asked a lot of very pointed questions about it. One of them was, how satisfied are you with your current AML infrastructure? And the answer is only 26% are very satisfied. But that leaves a lot of room for improvement. It means most people don't have kind of definitive architecture. We're not at the kind of VMware stage where you just pick VMware to run your virtualization and it's probably going to work out fine. We're not at the Wintel dynasty stage where you're just going to run it on there. We're not even at the fully developed Linux stage where you just say, well, we'll hack together Linux and do that. And that's kind of the best way to do it. So I'd say a lot of room for improvement. Only 55% are somewhat satisfied. And so that means folks are still building out what they want their perfect stack to look like. And when you're kind of choosing the stack, there is an old software dilemma that you face, right? And that's your build versus buy versus best of breed. And this goes back well before machine learning, but it has some new wrinkles in terms of machine learning. The first is really build your own. And this is, a lot of companies that pioneered this. You got Google and Microsoft, Tesla, OpenAI, DeepMind, Netflix, all these kind of companies. And because the field was new, they've really had little choice but to build their own stuff from scratch and to run their ML models in production. They really didn't have anything to pick from. They were largely pulling from academia. If you know anything about the AI winter, you know that they told a lot of folks, don't study this stuff. It's not going to work. And mostly because we didn't have the compute and the data sets really to put it into production at any kind of scale or to get it to work really well. So we knew the math worked, but it's not like physics where you can do theoretical physics and understand that it means something. If you can't actually build a model, it doesn't mean much. And so for many years, there was just a couple of folks, Jeffrey Hinton and teams out of Canada and various universities that were keeping the home fires burning on deep learning. And many people thought it would never work. It seems crazy now, but it wasn't that long ago that AlexNet started to use GPUs and you had the ImageNet competition, and we're kind of rapidly moving forward to things like, diffusers and the things that we're sort of dealing today, which is moving so fast. But it really is a very short period of time, and we're talking about essentially, not even 10 years. So the IA really doesn't recommend, and that's the AI Infrastructure Alliance. It's a nonprofit that we run. It doesn't recommend that most companies start to do that. Mostly your use case is not going to be unique enough, and you're building a lot of technical debt to do this. This is for incredibly advanced teams, right? If you're building a self-driving car company, or you're trying to advance the state of the art in something very specifically, and you've got former researchers from DeepMind and folks like that, yeah, you're probably going to build a lot of your own stuff. But if you're not that team, it's not advisable. You're going to build yourself a lot of problems. And by the way, there's just a lot of stuff out there that's worth checking out. The other one is kind of end-to-end solutions. So there used to be the old joke that nobody ever got fired for buying IBM back in the days, right? It was just a big, stable blue chip company. And in many points of the ecosystem development, you'll see kind of a single player kind of build an end-to-end system. The truth is there isn't really a full end-to-end system. We're still in the kind of early diffusion of innovation. And if you've ever seen that kind of famous curve of diffusion of innovation, there's kind of the pioneers, the early adopters, the early majority, the late majority, and the laggards. And we're very much in the early adopter phase of this stuff. There's parts of it that are very mature, and there are parts of it that are just not mature at all. So it's going to take a little bit of time before 2 or 3 platforms or a single platform is capable of doing everything from data engineering, cleaning, Q&A, labeling, distributed training, deployment, monitoring, management, inference, all these kinds of things in a single platform. It's too difficult to do at this point. If we get there, sure, absolutely buy that thing, but we're just not there yet as an ecosystem. The IA generally advocates the best of breed for medium to advanced data science teams. Again, if you have a very small use case, right? In other words, if you have very similar use case, if you're just doing churn prediction and things like that, yeah, you might find an end-to-end platform that kind of does those things. But in the general, if you're doing any kind of advanced fine-tuning of models, you're doing sort of more advanced machine learning and vision and large language models, any of those kinds of things, it makes sense to build a best breed. That means pick 2 or 3 core platforms that meet a wide variety of your needs, including data processing, pipelining, versioning, lineage, experiment tracking, deployment. And after you've kind of selected those core platforms, then it's easier to choose the satellite platforms. They're going to meet more specific needs. Maybe it's monitoring and management, those kinds of things. But once you've kind of chosen the core platforms, it's easier to pick the secondary ones because you know who they sort of integrate well with and play nice in the sandbox with. So, one of the things we saw in the survey was how long did it take for you to get the benefits from your AML platforms? And the good news is, a lot of people are less than a year, and some people are less than a year and a half, or 1 to 2 years, which is great. A few people are seeing 2+ years, 30+%, and some people the costs still outweigh the benefits. But the nice thing is that luckily in 2+ years, sometimes a lot less, you can kind of reap the rewards of building a good infrastructure. So that's incredibly positive for people. It means that if they spend the time to learn this stuff, pick the right things, right, that they're going to be able to choose a platform that makes sense. So how do we make sense of all of this stuff? The first thing is, whenever you see these kind of slides where there's 86 categories of machine learning that the marketing person invented, and they plug everyone's logo into a neat little box, these things are utterly useless. They're useless because they look really good. Everybody loves them. They retweet them like crazy. They post them on LinkedIn. But the fact is they don't actually convey any really useful information. And that's because these categories are usually never well thought out. They're very redundant. This is an old one, and there's lots of new ones. I'm sure you've all seen these slides a million times. But we spent a lot of time thinking about how can we distill this down to actually useful categories. And that takes some thinking to do. So one of the things we did was we built a blueprint for sort of basic infrastructure. We've got a newer version coming out. But if you look at it, it's basically broken down into these 5 components: data engineering engines, experimentation, training, deployment, and serving. And the thing is, then there's sort of data engineering orchestration, focused post pipelines, data engineering experimentation pipelines, monitoring. And you notice monitoring goes across a huge chunk of that, right? The data engineering goes across from here to here. Data experimentation goes from here to here. There's also these kind of data foundations like cloud and on-prem. There's secondary things like feature stores. The question becomes is this a perfect representation? No, but it's also something that really distills it down. And it's not one logo fits in here, but what it does is you can look at an example platform and say, look, we sort of partially support this really well. We completely support this, or we don't support this at all. And that's the truth, is that many people's platforms are evolving. They cut across a wide variety of the stack. And this is a much better way to visually represent the information. That's why we spend time doing that. You can check it out on the website. You can download it off GitHub. You can customize it to your own needs if you like. And then you can also see that multiple companies can kind of fit within it, right? So if you look at different companies with different coloring, you could see how a complete stack could come together with 5 different companies or 3 or 2. You can see where there's overlap and there's kind of a double shading there, right? And so these are the kinds of things that we spend a lot of time thinking about and looking at the space and trying to represent the information in a better way to help people make better decisions. So out of those different components that we've looked at, we've kind of broken them down into a few different things. One of them is orchestration pipelines and compute engines. So orchestrators are really the control engines. A lot of times they're kind of, we use the same term, pipeline, to control it, but an orchestrator is really the puppet master. The pipeline itself is where that is executed, and that's the compute engine really that's underneath. These are really the strongest contenders for being kind of your core platform choice. And there tends to be sort of two types of orchestration that people should pay attention to. One is a loosely coupled, and the other is tightly coupled. Both have their advantages and disadvantages. The basic advantage between them is pretty simple. A loosely coupled orchestrator is not really tied to the underlying execution engine. So Airflow is an example. It's loosely coupled. It doesn't have dedicated compute or scheduling. It does have a scheduling actually, but it doesn't have sort of dedicated compute. It's an outside scheduler, but it's loosely coupled. It means it can execute tasks along a diverse set of compute engines. A tightly coupled orchestrator is something that's tightly bound to the underlying compute engine, right? So Spark is usually a perfect example of this. It's both an orchestrator and it's kind of a big data distributed processing analytics engine, right? Now, the advantage of loosely coupled is that it can be an orchestrator of orchestrators. It can orchestrate across a lot of different platforms, right? If you've got a ZML or those kinds of things, you've got any kinds of Airflow and Prefect, these kinds of things, you can execute across a lot of different platforms. And that's usually great because you're probably going to have a diverse set of platforms under there. But the downside is that with the tightly coupled orchestrators, they're able to take advantage of underlying understanding of the compute, where the data is, how it's distributed, partitioned, those kinds of things. There's some loosely coupled that can kind of do that with plugins, but it's not usually as much of a two-way street as it needs to be, whereas kind of the compute engine can really signal things. So the downside, of course, is that most of the work needs to be done in that tightly coupled engine. And so if it doesn't do everything that you want, you end up kind of, with a loosely coupled orchestrator on top of that thing anyway. So really there's, again, advantages and disadvantages to kind of either of these two things. What are the components? This is another question we asked our different folks out there. What components of your AML infrastructure have the biggest impact on your results, right? And you'll notice the top two are very much data engineering. Excuse me. Collecting the necessary data, cleaning, transforming, QAing, and processing the data. Sorry, there, I have a bit of a thing there. Got it. Okay, so look, collecting the necessary data, cleaning, transforming, QAing the data. These are data engineering tasks. And these are the things that people are spending, they think have the biggest impact on the results. And that's really because of how machine learning systems learn versus how humans learn. They kind of learn in the exact opposite way, as you all know. Humans learn from a very little amount of data and can distribute it across a broad compute engine. We have lots of we have lots of neurons to spare. In machine learning, you tend to have a smaller subset of neurons with a lot of data. Making sure that data is awesome and clean, as we've seen through a lot of the different papers that are out there, the chinchilla paper, et cetera. The better the data, the better your model. And so transforming, QAing, doing all the kind of the dirty work there is really super important. And it's also reflected in the amount of data engineers that are being hired versus data scientists. So the composition is usually a 2-to-1 in terms of data engineers. And data engineers are kind of classically the kinds of folks that used to be in IT, and have now morphed into, dealing with the underlying Kubernetes and, and Ray and, the S3 buckets, right? The versioning lineage, the, Slurm, these kinds of things, any of those kinds of things that they're sort of dealing with, making sure that things are all stitched together, that they're performing well, that nodes are not going down. But they're also kind of cleaning all of the data itself, right? Maybe they're digging in and finding redundancies, or making sure that the latest snapshots are there, or running particular machine learning programs to strip out adult material or whatever from a crawled website, or toxic material, these kinds of things. That's where the data engineers are. Those are very important. So current trends in the next 5 years, orchestration and compute are some of the most essential components, and they're going to be a foundational bedrock for whatever you're doing. So when you're looking to make a decision with your team, you've got to look at the capabilities of your team. Do you have a lot of strong programmers, or do they need a powerful GUI, or both? What's the range of capabilities of the platform? What kind of problems are you trying to solve? Do you know? Or are you just looking at kind of the problems you have now instead of thinking about the problems you're going to have in 2 or 3 years if you're successful, right? And if you're just doing churn prediction and things like that now, are you really going to move into more advanced machine learning things later? What does that look like? Are you dealing with structured, semi-structured, unstructured data, all of the above? Many of the platforms don't really deal well with both of those in the same thing. It's very hard to shove, giant video files into a database backend, no matter what anybody kind of tells you in their marketing. Whereas, structured data with text, fits very easily in their database. What are the connectors and integrators? How's the customer team support? All these kinds of things are super important for your decisions, and you should weigh them all very carefully when you're looking at different platforms. Model deployment and serving are kind of the next big category of things that we looked at. And, there's a lot of traditional code-based application deployments that evolved in the last decades that are faster and more automated rollouts. AML is building a lot of those foundations, but there's a lot of wrinkles to AML that's just different from how it is in sort of a traditional web application. So if you look at something like when you roll out a model with a shadow deployment, right, where you basically, or in a blue-green deployment, in a traditional web environment, that blue-green deployment might only be up for a few hours or a few days, and then you're going to shut it down. A model might have to be in a shadow deployment or a blue-green deployment for a month. And you have to be looking at the different metrics and gathering statistics on it to make sure that it isn't performing much worse or doing things that you didn't expect it to do, right? So there's a lot of different things you have to really look at when you think of it. Now, Algorithmia found in 2020 that very few people were getting models into production in 0 to 7 days, about 14. And they reported that 28% of organizations took 8 to 30 days. Now, the nice thing is we found is that the numbers have in fact changed in 2 years later. Teams are getting better and faster at getting models into production. As many as 34% or 30 days or less, a week, 17%, 1 day, 5%. Some are still taking 2 to 3 months, right? And some are still taking 6 to 8 months. This is mirroring the kind of DevOps level kind of deployments that we're seeing now, where you're getting more elite teams are able to deploy it faster. But again, many folks are still struggling, and you'll notice that one of the things they answered is the hardest thing to plan for is operationalizing and productionizing a model, right? It's one of these things where you may be good at certain types of models, but then the dependencies or the inference is not fast enough. Those kinds of things when you start productionizing a specific model, the memory footprint is too high. It's one thing if you can run it on just standard CPUs. It's another if you have to run it on GPUs, and another thing if you have to run it on high-end GPUs, A40s, A100s, H100s. Those kind of inference engines can be very difficult to productionize, and you find that there's a big difference between academia and maximizing kind of the kind of benchmarks that you're hitting versus inference, how fast it is. If I have a model that's supposed to predict what I'm typing, like when you're in Gmail or Google Docs and it's predicting the sentence you're going to type, if it doesn't do that faster than I can type it, it actually doesn't matter how accurate your model is, right? And so these kinds of things become very important when you're thinking about operationalizing the infrastructure. When you think about deployment and serving, we divide them, really into two different, very specialized things. Deployment is the workflow that gets a trained model into production. Those are the steps. And then serving is really that inference. And these are two very different things. You shouldn't confuse them when you're looking at a platform. Most are going to specialize in both. But that workflow involves the human steps, the automated and the partially automated steps to package up that model and get it into production. And sometimes the loop back to it. It's not always a straight line. There's a lot of loop back, and especially if you got reinforcement learning and things like that. When it comes to serving the model, we're talking about a platform to receive and respond to those requests and predictions, right? And the software tools to maintain, manage, and monitor those platforms. And those are very different things. Again, those fold back into sort of traditional IT infrastructure, the same way you have maybe a distributed web infrastructure, and you're keeping your databases running and your web servers and your caching engines all running smoothly, and the same kind of thing that you're dealing with when you're dealing with model predictions and APIs and making sure the inference is happening in a set amount of time. So the next kind of category that we put together is what we're calling AI supervision. So we coined a new term for it, and that's because monitoring, observability, explainability are subsets and they're kind of three different things, right? They're subsets of supervision. The problem is a lot of times people end up just using the term monitoring or observability, and sometimes even explainability, but usually monitoring and observability to describe all three. and it gets very confusing. So in fact, we were even doing that when we were kind of working on initial versions of the report. So again, this is an example of how we kind of step back and think about something and say, hey, does that make sense? We don't just kind of accept, this is what people told us. It's like, no, we have to think about how do you categorize these things appropriately. And the reason we chose supervision is because it's this overarching thing of how you pay attention to your models. And typically, when you see monitoring, it tries to answer those questions of what and when. Is the web server up or down? Is the inference engine running? Is it responding in a set amount of time? When did it go up or down? This is most closely tracking with kind of traditional IT monitoring, uptime, performance, those kinds of things. Observability gives context into the how and why. The model went down because the last deployment created instabilities, or it used too much memory, or caused it to crash, or it was throwing CUDA errors, and it was down for 10 minutes, right? It's these kinds of things that helps answer the question why maybe the model's prediction performance is degraded. It could be earlier in the pipeline. You say, hey, wait a minute, it's focused too much. This fraud model is focused too much on age or something of that nature, and so it's missing a lot of things. And in the past, it shows a broader category of features to look at, and so the performance is degraded. And you want to answer those questions for yourself and why the models may be doing worse or better, right? So that's where observability comes in. It's not just reactive; it's also something where you're trying to query deeper into what's happening. And explainability is a suite of algorithms that helps humans understand why a model has made a decision after the fact, right? If you look at some of the algorithms that kind of tell you which pixels a computer vision model focused on, and you look and you see this hotspot showcase the cat with, you see maybe its ears and its eyes and its whiskers, and it focused on that when it shows the cat, or it focused incorrectly and labeled it a dog, because it focused on these sort of areas of the picture and where its attention went. So those kinds of things, explainability, those are going to become that's still very cutting edge technology in a lot of ways. There's a lot of companies like Anthropic and other wonderful kind of companies doing deep research, working on making models more explainable, and so they can kind of you can talk to them and understand why they're doing. I say talk to them. It's not Star Trek, where you're talking to the computer, but basically interrogating the model to understand why it did what it did or made decisions. That's going to be an ongoing area of research, but there's still a lot of explainability algorithms now that are helpful. But monitoring and observability is where people spend most of their time, and explainability is one of those things that's going to grow over the next couple of years. Again, I would say that you don't want to think of monitoring and observability as really the same thing as traditional IT monitoring due to its unique characteristics. And we kind of discussed those in detail in the report. But the short answer is, like, again, you might only care about the web server being up or down in terms of monitoring, and you generally don't care about the history of the web server unless it's been bouncing because of updates or something like that. Generally, you can throw the history away. But in terms of monitoring a model, a lot of times you do need a huge amount of the history to know whether if its predictions are along a clean baseline, or whether it's still serving those things accurately. And so there's a kind of different backend engines that are really necessary to make it a reality. And it's important to kind of understand those, if you want to, kind of draw the distinction between those two. So we go into a lot more depth in the report. Again, it's free; you can check it out. But it kind of helps you kind of draw a distinction between, Prometheus and Grafana and things like that, which are wonderful, absolutely useful. You're still going to have them, but there's like very specific sort of monitoring tools for prediction and things of that nature. Training is another major bottleneck, machine learning, alongside labeling, probably the two biggest ones. One of them, training, is dependent upon waiting for computers to do things. And the other one, labeling, is oftentimes waiting for people to do things. But they are largely the two biggest bottlenecks in any kind of machine learning. And so it's also one of the most complex systems administration aspects of a training. If you're doing especially distributions across systems, if you have something that fits on a single GPU, great, or on a single node of A100s or something like that, which has generally eight GPUs, or if you've got kind of a TPU management system with Kubernetes, and you can kind of work within the architecture that you need there. But many models need sort of lots of GPUs, lots of TPUs, those kinds of things, and it becomes challenging to kind of manage those things. It basically is supercomputer management. You worry as much about the interconnect and the networking as you do about the compute itself. which GPUs or kind of nodes have failed. How do you restart things? Monitoring management of those kinds of things. Training is incredibly challenging. And there's also how do models get parallelized in training? There's a lot of techniques that are sort of coming out, but it's most cutting edge. And there's been a number of companies that have focused on it, but in many ways, more and more we're sort of seeing like new approaches to how we kind of distribute these types of things. If you look at kind of our results from our survey, training models was the third biggest challenge that everyone faced right after all the data engineering aspects, right? So it's getting that data and queuing it and working it down, but then training it in a distributed manner is incredibly challenging. It's something I deal with every day with my team, and we sort of are always trying to find ways to maximize the networking, the bandwidth, how much memory the models are using, et cetera, and we're even looking at sort of alternative chip architectures at times to see whether we can deal with larger models, parallelize training in new ways. These kinds of things are need to be taken into account. The current trends in the next 5 years. Most organizations are not yet training a large number of models or training models consistently enough to generate advanced training capabilities. In other words, that of course this is changing every day. We get many companies that are starting to get to hundreds of models or thousands of models into production if they're an ML focused, heavy ML users. But many companies are just sort of dabbling in this, and it's difficult to justify sort of the advanced training capabilities. But if you are starting to deal with LLMs or diffusion models, transformers, all these kinds of things, if you're fine tuning models or you're doing continual learning, these kinds of things, these are where you start looking at organizations that need to have GPUs or tensor ASICs and more advanced techniques. There's a lot of frameworks out there. There's PyTorch Lightning, there's Horovod, TFX has sort of fallen off, but is starting to be replaced by Jack. There's a lot of skilled IT departments that can utilize frameworks on Azure Machine Learning and Vertex and Amazon and the SageMaker team there and those kinds of things, high performance compute teams. Those advanced teams are largely going to leverage either supercomputing in a box like Lambda or their own sort of NVIDIA DGX boxes, or they're going to leverage one of the public clouds and have an advanced team to kind of work on these things. This is going to be a work in progress over the next 5 years. The next thing to think about is data versioning, lineage, and metadata. So these are also terms that tend to get just tossed around. Metadata is really just kind of the data that sort of tells you about data, but it's kind of worthless without having kind of versioning and lineage, in other words, or immutability and snapshotting of that data. So the versioning is the snapshots of the data, really, if you think about it. And nowadays, in the old days, you had to take manual snapshots, or you had to take snapshots over time, but you had to describe what was in it. Now we can essentially take unlimited snapshots with a lot of the object stores that are out there. It's essentially infinite, or to us, even if it's the illusion of infinite, which means you can take snapshots indefinitely. The problem is, of course, if you don't have something keeping track of that lineage, like a versioning system or a Git-like system. Git is generally not recommended because it's really built for distributed systems and not for sort of petabytes of centralized data. But a lot of the systems take inspiration from Git and to keep kind of track of what's in the models, the data, as they're sort of changing kind of, and the code as they're sort of changing all at the same time. So lineage allows you to track what's in all those kind of snapshots over time and allow you to roll backwards and forwards. This is weirdly enough like a problem that most people don't know that they have until later. And so it's a thing where you often need kind of strong integration with the underlying compute engine, right? Because you really want things like immutability and the ability to in really advanced systems, you probably want copy on write file systems, but you're generally only keeping the pointers to the changes in the data. A lot of systems out there will utilize just copies of the data endlessly. That's pretty cool for smaller files, and it works really well. But if I'm working with video files or large image files, that are a gig a piece, and I change to a couple of small frames in the video, and then I have to make an entire gigabyte copy of that thing instead of just a pointer to the few bits that have changed. That's a completely different thing, right? And so it's going to depend on the kinds of data that you're working with. Immutability can be an incredible thing. If you just have a lineage tracking system that's keeping track of the metadata, but it's not actually snapshotting or copying the data. That's a problem too, because you could end up pointing to a set of data that kind of no longer exists, right? So if I have something like, 1,000,000 images in a directory, 1024 by 768, and then I run 50 training jobs on them, and then I go back as an administrator and I overwrite those images as 512 by 512, I can't recreate that data, those runs, those training runs, and I have metadata that points to a state that doesn't exist. So you really want to have something that's either copying the data or a copy on write file system, and it's doing that automatically. You don't want it to be a manual thing. If you've been in IT, you know that manual backups don't work. You're always going to forget, or you didn't do it when you needed to do it. You want it to be something that's kind of automatic. And again, most teams don't kind of figure this out until later. Then they find out maybe they get there's sort of a change in the laws, or they need to go back and find someone's face in the database, or they need to, if the EU law passes in the next couple of years, where you need to be able to go back and pull people out of a data set, or pull things out of a data set, or information out of the data set. If you can't go back and do it, you're going to be up the creek without a paddle. And so it's the kind of thing the team should be thinking about right now, even if they haven't thought about it already. There's kind of a couple different types of versioning, and there's kind of the DBs. Versioning of databases is incredibly new. There's a few types of things that are doing it, but generally when you're talking about versioning of databases, you're really talking about versioning of the schema, but it's always considered that the data is always hot and changing. It's only we're starting to see a few things where they keep kind of versions of databases, and it's not something that's generally done. It's starting to happen though, and you're starting to see new databases that are kind of able to do this, and they're going to kind of keep histories of the data. You can kind of hack it together with something like MongoDB, but you really want something that is focused on doing that kind of versioning. And then there's the versioning of files and object stores. That's got a long history in computers, in IT. And it's something that machine learning is essentially just building on. And so those are kind of the two different things that you'd be looking for in a platform. It's likely you'd have a division between sort of databases and kind of unstructured data, unless your unstructured data is very small. Shoving it into a database is a bit of a challenge, so you'll likely have a lot of these things sitting in object stores. Let's get to labeling. This obviously the process of adding tags and metadata to your raw data, your videos, your images, your text. And that kind of codifies the knowledge and features that we want the AML models to learn. Obviously, there's different types of learning. There's semi-supervised, unsupervised, supervised. A lot of the most important models in the world today are still very supervised or semi-supervised. Data labeling is one of the largest bottlenecks, and that's because historically the only good way to get good labels is to brute force through it or to crowdsource it. But recent advances we've started to see augment the manual data labeling by using machine learning itself. And so that's an interesting thing of like machine learning becomes reflective in this process. We start to see machine learning kind of speeding up the process of where there's sort of bottlenecks, right? And so one of the ways that they do that is sort of semi-supervised learning. I think we'll talk about that just in a bit, but you might label a data set with it's got 2 billion images, but you might label 10,000 of them or 1,000,000 of them by brute force, carefully labeling them, then teach a classifier to then learn those kinds of labels, go into the rest of the data set and do you a noisy label, and then use a human in the loop process to double check it. So that's where a lot of the advanced teams that are building things, you start to see the scales and the snorkels of the world, they're building kind of advanced tools to deal with those aspects of advanced machine learning. You'll notice it's the fourth biggest challenge teams are facing, latency and finding the right people being in the top two. Or inflexible architecture being the fourth one, and the third one. So remember when I said earlier, a lot of people aren't happy with their architecture, and it's maybe because they didn't think far enough into the future. They built the architecture for one thing and found out it wasn't very good for other things. So, but labeling is the biggest, the fourth challenge, and it's a close fourth there. So it's something you want to choose the right team when you're working on kind of large data sets. And again, most labeling platforms are going to have like the basic characteristics. They're going to have a manual workflow. It ingests data. It allows the teams that's local or distributed to add metadata. The labelers might put bounding boxes around something and make notes about what those things are. You're going to find that in every platform, from open source one to the most advanced one. But again, the advanced capabilities you start to see things like the algorithms. Again, it's based on machine learning. The algorithms start looking for consistency across different labelers, right? And then they might notice, wait a minute, labeler A is not doing a great job of labeling the fish properly. It might send that issue to a manager reviewer to reject or approve that and send it back to the labeler. There might be training, so those kinds of things are incredibly important. And then sort of the other things we talked about are again like the semi-supervised learning is some of the most important things that we're seeing, and I expect to see more advances there. It's going to remain a consistent bottleneck. Again, not all projects require labeling, but all labeling kind of exists regardless. If you're building something to detect whether someone left the shopping cart or not, the data basically says is the label, it's yes or no. But in general, a lot of the most advanced use cases are going to require labeling. And to have a strong workplace engine that is a clean understanding of the kinds of advanced use cases that are coming along to advance this sort of massively boring and repetitive task. You don't want to just try to crank it with your in-house teams. Like, great, we've got machine learning and they know it best, so we're just going to make them sit in front of the thing and crank it for forever. But that's not going to be a good strategy either. So you really need a good partner. You need really good, strong software to be able to do this consistently. We'll talk about feature stores. Feature stores popped up in a lot of different places. They seem to show up in everyone's charts over the last couple of years. But the interesting thing is that feature stores are a very specific use case. They're not necessarily for every single thing. They tend to be for structured use cases, although there are examples of it being used for unstructured. The challenge is when you're just looking at a string of digits, for a vector, you're not really able to make a good decision. Whereas a feature store that's based on structured data allows a large data science team to basically construct features and then pull those into other models without doing a lot of redundant work. So if I'm calculating the age of everyone based on the current day and time and their birthday and the year that they were born, we don't want 20 different teams doing that. We want to just be able to consume that. We want it to be as fresh as possible. And so that's where a lot of this feature store is going to come into play. They're really basically they're really kind of a new type of database. And there's sort of 4 components. There's a lot of confusion around this. And I think it's challenging to understand. Maybe it's because the marketing stuff sort of intentionally confuses it, but I'd say there's essentially 4 components of a feature store. There's 2 databases: feature catalog, transformations, and serving and supervision. So a data warehouse, a Snowflake or a Redshift, those kinds of things are really going to be where your basic foundational database is, and it's got a lot of offline features or things that you can pull features from. And then the second database is kind of a in-memory, low latency database that offers those features really, really quickly to models, right? And so that's really the magic of a feature store, is kind of that low latency database. And that's really where it is, but it's really pulling from a lot of other databases. So you want to look at the plugins and the ability of the databases that it support. And then obviously the next major component is going to be the feature catalog. What features are there? How do I browse it? How do I call it in a model? How do I call it programmatically in a model? How do I know that it's fresh or not fresh? These kinds of things. And how do I go back to historical versions of those features? Because maybe I don't need the freshest one. Maybe I need one from 2 days ago to compare things in order to calculate something I'm doing in another model. So that's super important. Obviously, the last one is supervision. Again, monitoring and managing the databases, make sure they're up in time, because if you're going to have this thing as the thing that has features for hundreds or thousands of different models, well, it better be up. And you better have a strong IT management and supervision group that's looking at that and keeping it up in real time. And then essentially the feature stores are either capable of 2 kinds of things, either batch processing or streaming. Streaming is relatively new, but incredibly important for companies like Uber and places like that. But batch may be good enough for you depending on what you're trying to do. The current trends is we've seen a number of kind of commercial feature stores come out. They're facing growing pressure from open source solutions. They're also facing competition from orchestrators with their own proprietary built-in feature stores. So commercial stores are good for large teams that need to guarantee response time, and they need dedicated support because a lot of things are going to be dependent on the feature store. And SaaS offerings are going to help kind of manage the complexity. However, they may not support all the desired backends that an organization needs. So you need to look closely at those backends. And open source solutions are good for smaller teams and teams that have excellent IT skills and teams that need to support a wide variety of backends or extend the platform on their own. But again, just like any open source solution, you better have the IT people in there to support it. Well, I think one of the last things we're covering here is synthetic data. This is artificial data. It's not gathered from the real world. It's one of the newest, and again, probably the most cutting edge domains in AI/ML. it's one where we basically are using machine learning to generate the data itself, which bypasses a lot of the other problems in terms of labeling, because you can kind of generate cleanly labeled data at the same time that you're generating it. Synthetic data is ranked as second in the things that teams I think are going to have the biggest impact in the years. These huge data sets where you need to crawl the web, there's ethical considerations, there's like just scale considerations that come into mind. It's a huge amount of work. You don't necessarily know what's in all the data sets. You've got to do a lot of cleaning and management of those things. Using machine learning just to kind of clean it, that's challenging. Or there's huge private data sets, which are incredibly challenging to purchase or to procure. Teams are notably difficult in terms of wanting to share those assets. So synthetic data serves the opportunity to generate a lot of those different things. The other thing is there's kind of different types of synthetic data that you want to think about. There's kind of the fully synthetic, means the data doesn't include any data gathered from the real world, generated entirely procedurally. Partially synthetic means that the data replaces part of the generated data. So you may replace sensitive characteristics, names, social security numbers. So the data is real, but you've stripped out all the other stuff and generated kind of dummy data within there. And then there's a hybrid synthetic, right? It comes from both real and synthetic data. You've taken real data, you've profiled it with machine learning, and you've essentially did an additional data set, a larger data set that's useful for training a model. You might see this in a lot of like manufacturing use cases, for instance. That's a classic example where you've got something that says, hey, I've got, I don't know, 50 million images of working widgets, and I've only got 2,000 images of broken widgets. Problem is, you've got a broken distribution, so you're really trying to detect when a widget is broken, and so you kind of need to generate more synthetic images in order to help augment that data set. And what's interesting about synthetic data is that visual data is farther. This is one of the answers where visual data is often further along than textual data. We kind of can look at a visual image and understand that it's real. If I want to generate, again, an example, if I'm trying to detect boat crashes, I probably don't have a lot of video of boat crashes, but I might be able to use the Unreal Engine or Unity or something like that to generate a series of boat crashes that I could use to train the data. And so, whereas if I generate a lot of part data, or I generate a lot of data for I don't know, financial transactions, I might not be able to generate all the clever ways that people commit fraud, right? And so it's more challenging with some of that textual data. So there's a lot of different platforms that are out there. I'd say it's poised to be a major accelerator, but it's also still currently in its infancy. It's maybe the earliest and the most immature, except when you're talking about visual data. But it does solve one of the biggest bottlenecks in effectively creating models, and there's going to be a lot of money and research pouring into this. We're advising anyone to kind of look at synthetic data to clearly understand what problem they're trying to solve. If you're in a financial institution, you probably have some robust choices to pick from, but if you're looking to invent novel fraud use cases that have never existed, you're not going to find much help there. So you really have to understand your use cases very clearly, make a short list of those teams, and then look carefully and critically at those offerings and the team that support those platforms. So that's it. Look, there is tremendous innovation happening in the IML infrastructure space, but with so many platforms in the ecosystem, look, it's just challenging for any one team to get their head around all of it all. Not all parts of the ecosystem are equally developed, right? We've got some really strong compute and orchestration. We've got some great monitoring and management supervision stuff. If you're but in some things like synthetic data, it's brand new and developing. Or if we're looking at labeling, we've got the basic workflow down, but some of the semi-supervised learning models and systems are still kind of developing along that. So you've got a whole bunch of different things that comprise this ecosystem, and they're at different sort of levels of maturity. And so you've really got to continually kind of look at the space, understand your needs, and understand where each part is. I would say the kind of last thing we looked at in terms of that's probably relevant to you folks is, how do you categorize your company? And what we started to notice is that more and more people are just digging into machine learning. The very few haven't started at all. A bunch of them 41% are using them in multiple areas of their business. 28% even categorize themselves as an AI first culture. And a rise that we're going to see in the coming years are AI driven business models. These are companies where the model simply could not exist without AML. I always use the example of generating photorealistic fashion models for an online catalog. If you've got 10,000 pieces of clothing and you want to showcase them all on a different human models, you wouldn't be able to hire enough models to showcase all those permutations but you could generate that with AI. And I mean, fashion models, not models, AI ML, right? But and then you could still hire humans to do, the big photo shoots and the awesome shoots that go on billboards, right? So that's an AI-driven business model. We're going to see the rise of more and more of those in the coming years. That's really, we're about at the end here, which is great. But basically, the growth of any sort of AML journey is that each stage you're going to need different tools. So don't expect that what you pick today is sort of baked in stone. The techniques are changing. The research is growing so fast. The tools are changing, and when you start off, you need simpler tools. But as your team grows, you need newer and better tools to deal with that growth. AI is really going to affect every single industry on Earth: telecommunications, finance, healthcare, defense, construction, manufacturing, agriculture. There really isn't a single industry anywhere that's not going to benefit from being more intelligent. Nobody is sitting around saying, "I wish my supply chain was dumber." They're all saying, "I wish it was smarter." So. But without the right infrastructure tools, organizations just can't build these world-changing apps. The AML infrastructure stacks of today and tomorrow will form the foundation that allows the intelligence revolution to happen. And as those tools mature, the entire industry moves forward into an early majority stage. We'll begin to see more and more applications that we just can't live without, and that we couldn't possibly imagine before, and that we couldn't possibly create with traditional programming. So AML infrastructure is really the infrastructure on which to build the applications of tomorrow. So that's it.
Soft clap. So thank you, Daniel. Before we get to questions, I want to give people a chance to type them out because I know it always takes a second. So I'm going to steal the screen from you for about 30 seconds, and then I'll have you reshare that last slide.
Okay.
All right. So just want to say, thanks for being here today. Next week, we'll have Dr. Selena Fisk. She is a data storyteller who is passionate about helping others sort through numbers to tell real stories and lead positive changes. But she's going to be giving us a talk on data storytelling. What does your data tell you? This will be on November 2nd, so literally 1 week from today at noon Pacific time, so just a little later in the day. And by the end of the session, we're going to be able to we're going to develop knowledge on using and analyzing data, how to effectively communicate and act on insights with our data. We'll talk about evidence-informed practice and the ideal outcome of data storytelling. So if data storytelling is something that you need more practice with, definitely think about joining us tomorrow. You can RSVP on our website or join one of our live streams on LinkedIn, YouTube, Facebook, or Twitter. All right, Daniel, that's all. And now we can jump into questions.
No worries.
Once I figure out where my
questions are.
Yeah. Sharing the screen always messes me up a little bit. Okay, Zoom, where are you?
Thanks for the kind words there.
So while I figure this out, maybe I can ask you one of the questions. So we have someone that's a little bit in disbelief that China is really beating the US for AI and ML research. I don't know if there's anything you can comment on with that.
No, look, this is this is really a qualified assumption. I think that a lot of the cutting edge stuff is still coming out of the States and in Europe, and a lot of the newest innovations are coming out of the big tech companies, right, and folks like that. But certainly, China, there's a tremendous advancement too. You have the Baidu team, and they've certainly deployed it at scale for a lot of different things. You have kind of city brain and those type of things. They tend to be very different in terms of the things that they're focusing on. But I don't think that's an idea that one or the other is kind of doing things better or differently. I think it's different. I think there's a focus. I think both both sides of the pond, if you will, are basically doing advanced research, and I think that's going to be a push-pull for forever. I think everybody in the world knows that artificial intelligence is one of the most important things for the coming decades, and everyone wants to have an advantage in it. So I think everyone's going to continue to kind of pour their resources into it because it's super important, and nobody wants to fall behind in it. And I expect you're going to see kind of huge advances in one area and then sort of falling behind there. We're certainly seeing in the chip wars right now, where much of the world hinges on Taiwan Semiconductor, right? And they make some of the biggest chips in the world, and then you see sort of the CHIPS Act and kind of denying China the larger the more advanced chips. But there's definitely a push and we're going to see this kind of play out over many years, but certainly I don't think anyone has a definitive advantage at this point.
Okay, great. And then, so we had some people who they kind of got lost when you were talking about data lineage. So what is recommended for data lineage specifically? I think you were talking about something that was better than Git.
Almost all the platforms are going to be inspired by Git. I think there's only one or two platforms that actually use Git itself. The problem is, of course, that Git was made for distributed data science teams, or not distributed data science teams. It was made for distributed coding teams, and code is much smaller than data. And the idea is that if I have all of my code syncing down to every laptop across the world as I'm coding the Linux kernel, that's fine. And I can keep track of kind of the snapshots and the lineage of how that code changed over time, right? And I can roll back to an earlier change. But if I'm trying to sync down, I don't know, 50 terabytes, petabyte of data to everybody's laptop, I got a big problem. So the challenge is it's generally going to be centralized of that data, and it's going to take inspiration from what Git did, which is hashing the different changes over time so that you can roll backwards and forwards, right? As many different teams are making changes to that. That's really what the lineage is. What is the journey of the data? Where did it come from? How has it changed over the course of time? That's really what lineage is. So you'll find that the vast majority of tools out there, when you look at Pachyderm, ClearMel, Equasio, a million ones that I can think of, Databricks, all of them are going to use kind of an inspiration in general from kind of, they learn from Git, but they're going to centralize the data and they're going to, take inspiration from it. But certain things you don't even need with Git. You're not going to do a binary diff. And first of all, you're going to run out of compute and you'll be waiting till the end of time to do a diff on, a million, 1 gigabyte video HK files, right? But also it's not going to tell you anything. Oh, well, this bit changed over here. It doesn't tell me that I don't know, scene 2 in the movie changed, right? So it's not very useful. So there's a lot of things you want to take inspiration from, but again, using Git itself, generally not a great strategy.
And we have a ton of, or I shouldn't say a ton, but quite a few questions on synthetic data. So let me know if we should save them. I'm just going to rattle them off. Let me know if we should save them for a little later or another time.
Yeah, we can always follow up if we needed to. Yeah, sure.
So how do you generate synthetic data? Is there a library that can do that?
There's a bunch of libraries out there that can do it. Again, so there's a couple ways that synthetic data is generally generated, right? Typically, when you're talking about textual data, right? There's going to be libraries that are out there. There's things like YData and a few other things. You can Google them. There's about 100 different libraries. Some of them are well maintained, some of them not at all, and we're just totally experimental. But there's a number of libraries that are basically like either are going to generate kind of totally procedural data. You're going to tell it the kind of data that you want. And it's going to generate it, or you're going to do what's called a lookalike data set. So it's generally going to say, hey, here's my data set of heart disease patients, and I want you to go. Essentially, the algorithm goes and does machine learning on that data itself, extracts the features of heart disease, and then basically uses that to procedurally generate additional sort of lookalike data of that kind. Or you might be fraud data, right? And you're going to go ahead and generate. Okay, I've looked at all the fraud data. It's really programmatic from an ethical standpoint or from a privacy standpoint to share that data. But I could look at the data, understand the features, and then generate synthetic data that has the same features, but doesn't actually include your name and my name and our social security number, right? So those kinds of things are incredibly useful for generating. And then the last one is sort of the visual kinds of data, as you said, mostly programmatically done, but you use engines like Unity, Unreal, other engines that are specifically built for this. Again, if I want to generate images or videos of boats crashing and then label them, I could, write code essentially to generate lots of different versions of, the boats hitting each other, right? And then, take sort of screenshots of those things over time and then have, labelers put them in there. So it's really kind of use case dependent, but you want to think about it as sort of the application of machine learning and or procedural code in order to generate synthetic or semi-synthetic data.
So building off of that, how would you check for data quality or integrity with synthetic data?
So there's a number of sort of data quality libraries out there that kind of look at it too. So Sorry, there's a combination of that. Let me just tell someone I'm going to call them back, or they'll call again. Hold on a sec. Call you in 10 minutes. Okay. On a webinar.
By person, in case they're watching.
Yeah, so I put it on Do Not Disturb, but a few people have starred contact,
Yeah.
and the starred contact got through. You do want starred contact so that emergencies can get through. But look, the thing about it is I was distracted. How do you so there's data quality engines that are kind of looking at these things, but a lot of it is sort of the code that you need to look at, right? So we're talking to Active Loop, for instance, they've got a system that kind of goes through and it builds kind of a catalog of all the data and allows you to quickly query it and visualize it, right? But you might be able to go and do random sampling for the data or write code to kind of look through different pieces to surface it to a human in the loop person to look at it. You might have classifiers that go through and look at that data itself, right? You might be looking for certain kinds of things you don't want in there. And so again, the applications of machine learning, once again, it's turtled all the way down, right? In terms of your ability to do it. And then obviously kind of human in the loop sampling of that data itself, being able to kind of visually inspect it. Sometimes that's easier. Again, once again, this is an area where visual data is far ahead of synthetic data, because if I ask 500 people, if I ask you to look at 500 samples to ask whether like a 50 character string looks legitimate, are you going to be able to tell me that it actually has 50 characters every time and that string is legitimate? And how would you even know? Or are you going to catch every example of a social security number or a 50 string Bitcoin hash or whatever it is that you're looking for in there? You're going to miss it. Whereas if I look at an image of a boat crash, I go, yeah, that kind of looks like a boat crash. Next, right? And so there's a lot of these types of things that we look at, and plus again, you can kind of sort of feature engineer, you can kind of do a lot of machine learning itself to kind of look at the data too and classify it. So classifiers become very important.
Okay, and then one final question before we end here. Can you talk about how you would approach diversity in the fashion model example? This person used to work for a catalog company, and they think they would have liked perhaps 100 models featuring different sizes and shapes, but not 10,000 models.
I mean, I'd say it's fairly easy, actually. I think this is one of the easier problems to solve, right? I think there's two types of ways that people look at it. They say, well, should the default prompt deliver diversity? But if you look at something like Stable Diffusion, there's a great post on Reddit where someone generated like 180 different ethnicities of mother by asking for that ethnicity. And it's beautiful, right? It's just a wonderful collage. And so I think that what you want, the best way to kind of address the diversity thing is specifically ask for it and know that it's important to you and your company, right? And to say like, I want people of different size, shapes, ethnicities, genders, I want trans folks in there. I want all kinds of things. These are super important to me. You ask the model for it. And so the model itself has to have been trained on a diverse enough data set to be able to generate that. But I think actually many of the models already are starting to get there. And if not, you could certainly train the model to be fine-tuned to have a much wider diverse set. And I think that that's actually the best way to approach it. And if it's important as a company, you just go ahead and you say, I'm specifically asking for, ethnicity, gender, 747 pilot. I think that's the best way to address it. Then you get exactly what you want. There's some downside to doing it the other ways, right? Where you kind of do text prodding, prompt padding and things of that nature. So like, it gets some weird side effects. Like if I'm asking for, Super Mario in the real world, I want an Italian plumber, right? And that's fine. I don't want the prompt changing it in the background. So I believe that the best way to do it is to make sure that you've trained a diverse model that reflects kind of the world and the beautiful kind of wonderful rainbow that it is, and then specifically to ask for those things and to know that it's important for you as an organization so that you get that diversity.
All right, perfect. Well, thank you, Daniel, and thank you everyone for being here.